Hello, hello, hello. How are you doing today? Turn that music down to that. How are we doing today, George? It's nice to see you. Look how it is. Look how it is. Look what it is. Look how it is. Oh my God, Connor, look how it is. I can't believe how it is. That's unbelievable. How you doing, buddy? It's ah, goodness, goodness. It is midnight if it's like that. I hope you're doing good, buddy. Getting ready for the last class of the night. Doing fun things. At least doing fun things. At least I think they're fun. Question mark, question mark, question mark. Let's see. That's what I got on the docket here for today. Just curious how many more weeks I have to go. Oh wow, I got more time than I thought I did. Okay. Perfect. I got a lot of time. Woo. Ooh, I have more time than I thought I did. Alrighty. It's midnight. I walked to 10K. Great. Had a Zoom training session. Excellent. I need sleep, but not tired. Makes sense. Yeah, it makes sense to me. You walked to 10K. Dang. Impressive. A little cold over here to walk a 10K. But I respect it. Yep. Need a drink today. Nighttime, daytime. Anytime is a time. Oh my goodness, we have some. Hopefully, we have some more people joining us here. We got. Ooh, yeah. Like the vibes here. This song pretty good. Yeah, anytime is math time. You know how it is. We gotta learn our maths. We gotta learn how we can apply it to the real world. We gotta learn legit things with legit people. That's just how it has to roll. Fun times, my friend, fun times. This is like I get to goof around for a little bit. What's wrong with that? I get to teach math at the same time while I goof off? That's the best! I ain't gonna lie. Whew. maybe I should. I'll eventually do that. Why not? I'll eventually get around to it. How's everybody doing today? I hope everybody's doing great on this wonderful, wonderful, wonderful afternoon here in Chicago. The Chicagoland area, I guess, is the more appropriate thing. Or if you're in the UK, it is almost at the stroke of midnight. Alright, hopefully you're having a nice time out there. Hopefully you're having fun. And most importantly, I hope everybody is safe and warm in their beds. Alright, or if you're not in bed, hopefully safe and warm in your homes. There you go. Not too bad. At 9:21, it was the 21st of January this year, 21 minutes into the 21st hour of the 21st day of the 21st year of the 21st century. I can respect all of that. This is very true. This is very true. I'm just glad I made it that far to have that fact thrown in me. I made it this far, my friend. I'm very happy with that. You're just like, wow, how did I get to be this old? Be like, oh man, I'm just happy to see these milestones. Daily fact. It is a daily. Wait, but it's March the 1st. Wouldn't you want to say that like on the 21st when it happened? Or the next day? I don't know. It's still a fact though. This is true. We don't. That's fair. That's fair. That's fair. That's fair. All right. Interesting name. Am I doing? Okay, then I have to use the. Wait, is that the binomial? The binomial distribution. Okay, that isn't. It's actually pretty. The binomial distribution. Oh man, that's so hard. As in, that is so easy. Not a problem. It's not a problem whatsoever. Outstanding cookie. Nom nom nom. Alright. Wait here for a few minutes and we'll, You in the mud? Hey, you stay safe there, Connor. You have a wonderful night, okay? Take care of yourself. Rest well, my friend. Rest well. Wait a couple minutes here, then we'll probably get going here. Hopefully we'll have a few more people come on in. And, yeah, we'll get started. Not too shabby. Alright. Hey, there she is. How are you doing, Susan? How are you doing tonight? Hopefully everything's going really well. I hope you had a great weekend. That's one thing that I hope you had. Hopefully it was chill. You got to chill up. Just finished dinner? Are you? Yeah, well, I'm just Yeah, I finished dinner myself. I didn't have a lot for dinner today, but just had some KFC. But the quick meal, the only thing I'll eat today. But that's not a problem. I have good times. I am doing very well. It's been positive vibes all over the place today, Susan. Lots of great positive vibes, lots of great positive people, such as yourself. So we're doing okay here. Nice pick. Yeah, my weekend I went quick as well. I spent some time with my mom for the weekend, just taking care of her. My sister went on a little mini vacation. There you go. My sister went down to the Dominican Republic to take a few days off. So, which she needed. So, to be fair, she needed a few days, and there you go. Mazdy, back to another hard day's work at math. You betcha, my dude. Absolutely 1,000%. We are definitely back to hard work at math. Definitely back to hard work, or hardly working, because, well, I don't technically work. I just kind of goof off. And then somehow, some way, magic things happen. I wave my hands, and then all of you learn math along the way. And that's just pretty much what happens. Okay? Semester passes, you're like, what the heck just happened? Be like, yup, there you go. Yeah, it does, right? So the exam is out of the way, right? So no more exam stuff to really worry about for a little while. So yeah, we're on really good pace here to where we want to be. So I'm pretty happy with that. Camera, hello, how are you doing? Do you guys not like the exam? I mean, it was a fair exam. I tried to be as fair as possible. Natty, hello, how are you? I hope you're doing well. Very good, very good. Today is a nice, wonderful day here. We are doing really, really well. It's a great exam, but I'm happy to know the results of a month's worth of work. Yeah, there you go. There you go. Yeah, I know the exams don't come by often, every 4 chapters or so, but yeah, it's been pretty good. Pretty good. Pretty good. So you guys worked really hard. I've looked at some of the results there, but not all of them, but some of them. Why is it so dry in here? All right. I don't know why it's so dry in my place. Someday I'll figure this out why it's super dry, but my nose is like the only thing that. All right. All right, ladies and gentlemen, let's get going here. Let's get to work. It's all right. Okay, let's get started today. Welcome back to Monday. Hope you're nice weekend. All right. So today we are going to be continuing to move forward here with Chapter 5. We're going to end Chapter 5 here today. So today is the last portion of Chapter 5. We did we did section 5.3 and 5.4 last time. Talked about in Chapter 5 here the rule of complements. At least we've talked about that as well. Talked about the general multiplication rule, general addition rule. Talked about those things there. Now today we're going to be doing something a little bit more fun. All right. So today is a nice, fun day because today's section here talks about our good friend counting. Okay, today we're going to talk all about counting and how to figure out probabilities behind counting. Okay, so counting here is going to be, say, not exactly 1, 2, 3, 4, 5. Maybe that's pretty basic counting, but we're going to count how many ways we can do a certain task in a given certain scenario. And it has a ton, and I do mean a ton of applications in real life. I'm going to take a look at a few of them here today. So That was definitely one of the fun things that we can do here in Chapter 5. One of my favorite sections in Chapter 5. So let's get to it. All right, so let's go to the big board here. We'll go to the big board. Yeah. Alrighty. All right, ladies and gentlemen, here we have what are we going to be doing today here, at least in these couple of sections. We're going to solve using the multiplication rule. We're going to talk about permutations and combinations. We'll solve some stuff using permutations with non-distinct items, so we'll talk about that briefly. And then, of course, the more important part is computing probabilities involving permutations and combinations. All right, so let's talk about the very first thing here. By the way, I'm so sorry, everybody. Does anybody have any questions about homework or tests or anything like that? Or anything for that matter? Any questions at all anybody has? Hey, Holly. How are you? Did you fix your problem there, Holly? I hope you did. I hope everything's fixed and ready to go. You can get your stuff done there. So, massive errors abound, I could tell. Yes, yeah, that's true. You did. That's true, Natty. You did. I understand. Look, I'm sympathetic to the cause. You know, I follow through with my promises. Should be good? Okay, good. Hello, Diana. How are you? I hope you're doing really well. Yeah, I got a question. If you got any questions, Diana, please feel free to ask, okay? All right. So, let's talk about. Oh, wonderful. That's good to hear. Hey, I want everybody to be safe and healthy. That's the most important thing. No, no, that's fair. No, that's Natty. That is fair. That is fair. I will be making an adjustment in relation to what I've said. So, not just to you, but to everybody. So, because that question was phrased that way, I will make that adjustment for everyone. So, um, yeah. So, for the test there, yeah. So, let me go ahead and make that announcement here really quick. So Natty shot me an email and said that one of the answers to one of the questions was talking about the type of variable was like a nominal. It was supposed to be nominal and ordinal, but it also had interval and ratio. And one of the answers was interval, and it was meant to be a nominal and ordinal question, but it fortunately was one of the things that we did not talk about. And so because that question had the potential to be something that we did not talk about, interval and ratio, I will be giving everybody credit for that particular question. That will go across the board. So like I said before, if we don't talk about something, but there's a question on the test that has something that we didn't talk about, um, the best fairest way that I can handle those type of situations is giving everyone credit for that question. So everybody gets everybody will get that adjustment there once I put it in the grade book. So I will make sure that that will be put in appropriately. So I'll put it in like some whatever the percentage is for that. So yeah. So want to be sure that everybody is aware about that, and be sure everything up to date. So whatever your score that you did get on the test there, bump it up like another be a percent or two. Um, and well, I gotta still make the adjustments there in the grade book on D2L. But once I go ahead and do that, you'll see your final score. But yeah, whatever you got on the test there, bump that up a couple, maybe a percentage point or two, and then that'll be probably your final score. So All right. All right. In any case, let's go ahead and talk about the fundamental principle of counting. All right. So, what is the fundamental principle of counting? So, the fundamental principle of counting is this: it says if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, the number of ways the task can be done is P times Q times R dot 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 ways. All right. So let's talk about a practical example of this here. Now, okay. So let's do a simple example here of the fundamental theorem, and then we'll just kind of work our way up with this idea. Okay. So let's say, for example, here you have to dress yourself. Okay. So let's say you have to dress yourself, and you have choices of what you want to wear. So let's say you have 7 shirts. Okay. Let's say you have 10 pairs of pants. So you have 10 pairs of pants. And maybe you want to look like extra cool. You'd be like, okay, I want to look super extra cool, but it's just like that. So maybe you have like 5 hoodies, okay? And you got to figure out, well, how many ways can I dress myself given this is what I have in my closet. So this is what I got in my wardrobe. Be like, I got 7 shirts, 10 pants, and 5 hoodies. How many pants do I have? How many pants do I have in my? How many jeans do I have? That's actually really the question. I got like 7 pairs of jeans. Something like that. Anyway, um, all right. So this is basically using the fundamental principle of counting. Okay. So essentially, you have to. Yeah, look, I don't got like the biggest wardrobe ever. I got a bunch of stuff in my closet from like a long time ago, but I still have like a box of clothes that I had from like when I used to wear like 10 years ago that I want to give over to Goodwill or something like that so other people can wear it. So I have one of those flannel shirts with the flannel thick shirts that people used to wear. I still have one of those that I would like to give to Good. Those things are good for the winter time. Um so the thermal flannel sweater shirt things. Yeah. mm, yes. Pretty nice though. I ain't gonna lie. They were nice back in the day. Anyway, so if you see here, how many choices do we have for the shirts here? So for the shirts here, we have 7 choices for the shirts. How many pants do we have? We got 10 pairs of pants, and then we'll multiply that by 5. So then, how many ways can we dress ourselves given this combination here? There's 350 ways to dress ourselves. Okay, so we have just 350 ways to dress ourselves at the end of the day, and there you go. Not so hard. So on the basic level, this is how we deal with the fundamental principle of counting. Now, having said that, however, we need to take this a little bit further. All right, let's talk about uh, let's talk about ice cream. Let's talk about ice cream. So let's say I wanted 3 scoops of ice cream. And mind you, I don't eat ice cream that much, but maybe you do. Okay, which is fair. All right, maybe I want 3 scoops of ice cream, and I want 3 different flavors because you know what, variety is the spice of life. Because that's what I want. Or I want 3 different flavors. Right? What I want. Now, let's go the old Baskin Robbins route. Now, if you know anything about Baskin Robbins is a company that made ice cream that merged with Dunkin' Donuts. Dunkin' Donuts bought them out. Okay, so that's why you see Dunkin' Donuts, Baskin Robbins. All right, but the original Baskin Robbins here was well known for their specific amount of flavors. In this case, their original 31 flavors. Okay, when it was its own separate independent ice cream shop. They're well known for their 31 flavors of ice cream. So, let's talk about how many ways we can build how many ways we can build three different flavors here of ice cream with three different scoops. Okay, so let's look at each one here. We'll build a little picture. All right, gonna go with this here. Let's go with the first scoop, second scoop, and the third scoop. Okay, so let's look at the first scoop here. How many how many choices do I have for the first scoop of ice cream? Go ahead and put that in chat here. How many choices do I have here for the first scoop ice cream? What do you guys think? I have 93? You're thinking 31 plus times 3 here. That's not exactly what I have here, camera. I'm just asking, how many choices do I have for the first scoop? All I have is 31. I have 31 flavors, so all I have is 31 choices. That's it. Simple as that. Okay? Let's just keep it basic here. Choices, I have 31 choices for the very first scoop of ice cream. Now, yeah, that's fine, that's fine. Okay, now I have the second scoop of ice cream. However, I don't want the same thing that I just had before for the previous scoop. So I don't want the same one again. Okay, I want a different flavor of ice cream. So how many choices do I have for the second scoop of ice cream? Well, I have 30, right? Okay, good, right? So I have 30 choices for the second scoop of ice cream, right? Because now I didn't want the same one as before, so now I only limit myself to 30 choices. That's fair. Okay, fine. Now I pick the third. Now don't want the previous two, right? I don't want the same flavor as the previous two. I want a different one. So that's correct, Jumpman. That's right. 29 flavors is what I want here for my third scoop, right? I want 29 flavors for my third scoop. So, in reality, how many possible ways can I make three scoops of, let's say, different flavored ice creams for each individual scoop? Well, the way I want to do that is 31 times 30 times 29. Okay, of course, calculate. And that is correct. 26,970 ways to build three scoops of ice cream, of which they are unique. Okay, so went ahead and found out how to make how we can make three scoops of ice cream in that instant. No problem. As you see there, yet another way to actually go ahead and showcase the application rule. Go ahead and take a look at one more here, at least on this end. And this guy, not in the book. All right. So let's think of license plates. Okay, let's think of license plates. Let's say we have a license. We want to make a license plate. We want to figure out how many possible license plates can we actually have. And let's say, according to an Illinois license plate, I believe you can have up to 6 or 7. No, sorry, 7 or 8. Illinois. Eight. Of 6, 7. So I think we got 7. Maybe it's 8. I think it's 8. Could be wrong. Oh, here. Oh, okay. So there's 7 actually for this one. All right. Well, that's fine. Okay. Looking that up there. All right. So let's go with this premise here for this example. All right. So Illinois license plates can have seven spots. Okay. It could be alphanumeric. So alphanumeric meaning you can have 0 to 9, or you can have A to Z. Okay. So 0 to 9 or A to Z is pretty much how we have here for our license plates. Now, real question is how many possible license plates do we have? All right, so how many possible license plates do we have? So we have 7 spots that we can place an alphanumeric digit into. Okay, well, how many possibilities can we put in for the very first spot? Okay, how many possibilities can we put in for the very first spot? 36. That is correct, right? We have 10 numbers here between 0 and 9, and we have 26 letters here between A and Z. So we have 36 possibilities of what we want to put in for the very first spot on our license plate. How about the second spot on our license plate? How many possibilities do we have then? How many do we have for the second spot on our license plate? How many possibilities? 35? Still 36. Okay. I'm going to agree with 36. I didn't say that they didn't have to repeat. They can repeat. For all I know, well, understand this, Natty. For all I know, I could have a license plate that exists as 1111111. I can have that number repeat as many times as I want. Okay, that is considered a valid license plate. Even if it looks silly, it still counts. Okay, I can have 7 A's. I can have, 7 B's, whatever the case may be. Maybe 7 B's reflects my actual grade point average, but you know what I'm saying. So, I'm a B student. Facts indeed. All right, so every time down, I'm going to have 36 possibilities for a license for each one of these spots since I have a chance to repeat. So my answer here is going to be 36 to the 7th power for the amount of possible license plates that we can have. So this is a pretty large number here. This is 7.84 times 10 to the 10th power. So I'm just kind of rounding in that case. So this would be, well, I know it's more than that, but still, this is a pretty large number here. So you're talking like a little over 78 billion possible license plates that you can make for automobiles, right? Pretty sure that there's more than 78. Pretty sure that there's less than 78 billion type cars here in the United States, or heck, even in Illinois. But this is a way we can actually uh, figure out how many possible ways we can how many possible license plates that there can be according to the rules of Illinois. Okay. It's the same thing for Social Security, by the way. There's a billion possible Social Security numbers. So that uses the same reasoning as we've just talked about here. All right. Any questions about that? Any questions? No? No? No, sir. All right. Good stuff. We're in good shape here. Everybody, we're in really good shape. All right. Halfway there already. Well, okay, maybe not totally half. Yeah, we'll get there. All right. I got more to talk about for sure. Let's talk about it. All right. Next. All right. So what we need to do next is we're going to talk about next what we're going to talk about here is number 2. Okay? So for us to kind of set us up for the remainder of this section here, we need to know one very important thing, and that is factorial and its notation. So what is factorial and its notation? Now the notation here for factorial is going to be the exclamation point. So the exclamation point here in math represents factorial. So we would say n factorial, for example. So how do we go ahead and what is n factorial here? Well, that's n times n minus 1 times n minus 2 all the way down to 3, 2, and 1 here respectively. So for example here, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. You can multiply that together and you get 120 at the end of the day. Also, I put this little side note here because it's sometimes used calculations that 0 factorial in mathematics is equivalent to 1. That's just a rule that we use here. It is an important rule here. So a general rule we use here is 0 factorial is 1. All right. Okay, so where are we going to use these factorials? Let's take a look here at number 3, see where it fits. Number 3 says, what is a permutation? All right, so a permutation, go ahead and read this off here. A permutation is the number of arrangements of R things chosen from a pool of N things where order matters. Okay, and here we see the notation. The notation here is NPRP, representing permutations, is equivalent to n factorial divided by n minus r factorial. And you see here n minus r done before the factorial part. And repetition is not allowed. Okay, now just as a side note here really quick, the n is going to be the pool. Okay, so it's going to be the bigger number and r will be the smaller number here. So n is the bigger number, r is the smaller number here. So be sure that you know you put those numbers in the right order. Bigger number first, smaller number second. Okay, but let's do an example like I have here. I'm going to do example 47 here together. And we're going to see exactly how we can tackle some of these problems. Tackle them, take them down. All right. Back to this book. Okay. Alrighty. So let's look at 47 here. All right. 47 says forming a committee. Okay. So 4 members from a 20-person committee are to be selected randomly to serve as a chairperson, vice chairperson, administrative assistant, treasurer. First person selected is the chairperson, the second, the vice chairperson, the third, the administrative assistant, and the fourth, the treasurer. Many different leadership structures are possible. Okay, so in this instance here, we need to figure out how many possible ways we can form this 4-person committee, in which case I pick the first person randomly. That person is suddenly the chairperson. Second person I pick is the vice chairperson. The third is suddenly the administrative assistant. And the fourth here is going to be treasurer. Okay, so what we want to do here in this instance is that because each person is going to be slotted into a particular position, that means that order matters in this particular instance. Okay, so when we talk about permutations, we have to answer the question, does order matter? And here in this instance, the answer is definitely yes. Order absolutely matters here, okay, because of the fact that, you know what, I have to put in these particular people in these particular positions, all right, based on what we have here. Now, we have a pool of 20 people that we're selecting from. So n here for 47 will equal 20. That's going to be the pool of people we're selecting from. How many of them are we selecting? Well, that's going to be 4. We're selecting 4 people out of those 20 people to make up this committee. What we have here is 20 permute 4. That's what we're going to have here in this instance. Okay, so let's use our formula here that we have off to the left. We're going to have 20 factorial divided by 20 minus 4 factorial. Now again here, we do have to do 20 minus 4 first before we apply the factorial. We're going to have 16 factorial here at least to start with. Okay, so we're good there so far. Okay, all right. So now, how do we solve for this here? So here, remember how factorial works. I want to do this by hand. This is the way you want to actually approach this. So you have 20 times 19 times 18 times 17 times 16 factorial. And you can actually divide that by 16 factorial. The reason why this works here specifically is because it goes 20, 19, 18 all the way down to 1, but 16 factorial just represents 16 all the way down to 1 anyway. Pretty much what happens here, which means that you don't have to do as much work here. You just cancel out the 16 factorials here, leaving you with 20, 19, 18, and 17. Okay, so if we do that out, here we get 116,280. All right, and that will be our final answer to this problem. All right, really quick, any questions about that here so far? Okay, want to be sure everybody's on the same page here. Okay, so one thing I want to point out here about this problem is pretty much the same type of problem as the ice cream problem. Talked about ice cream. Okay, the ice cream problem that we did here at the very beginning of class is directly correlated with this question as well. Okay, again, why is that? Well, because of the fact that in the ice cream question, order also did matter. We wanted to pick 3 unique flavors of our scoops of ice cream in that problem. And it pretty much works off the same permutation as exactly what we've done here. Again, you could easily get the same answer here by just drawing our little boxes here. Just saying, okay, I have 20 people to select for the chairperson. Now I have a pool of 19 for the vice chair. I have 18 for the administrative assistant, and I have 17 here for the treasurer. Okay, and you'll end up with the same exact answer as what we have up above. If you multiply them, again, it will be equal to 116,280. Okay, so there's multiple ways to arrive at the same answer here. This is the reason why I did the ice cream problem here, was because of the fact that you indeed get the same result regardless of which way you decide to go. Permutations here, at least in this case, if order matters, I know to use permutations. I will get this result. Some people like to draw a picture about how many choices they have in each particular spot. And in that case, then we go ahead and we can do that as well. So again, a couple ways to approach the same thing. Just wanted to show you 2 different. So, okay. So it's not too bad. It's just takes a little. All right. Now one more thing before we move on to the next example here is you have your calculator here. You might want to take it out right now. So let's take out our calculators here. You have your graphing calculator. We're going to go ahead and use that here in this. All right. So now in this case here, second. Oh, I just don't want my head to. All right. So okay. So what we want to do here first is, in order for us to do this on the calculator, what we're going to do is we're going to do 20 permute 4 here on the calculator to get the same answer that we had from 116,000. So this works for either old calculators, new calculators. You're going to do the same exact thing regardless. So let's go through this together. Once you go ahead and type in 20, okay, so we're going to type in 20 since that was our pool from our problem here. So we'll type in 20. All right. Next, I would like you to hit the math key here. Go ahead and hit the math key here. And I want you to go over to this subsection here that says PROB for probability. So if we scroll over to that section, we can see the options here of 2, 3, and 4. So the options here for 2, 3, and 4 are the 3 options that we're going to primarily use for this section here and for other sections probably. That is, first of all, you have NPR, which was the notation we talked about permutations. NCR here we'll talk about here shortly, which is the combinations here. And then, of course, the factorial notation should you need to use that. Now, we're more interested, of course, into NPR, the number of permutations. So, as you can see here, it has put that 20 already in place. And then we're going to go ahead and hit 4 here as our ending point here. We have 20 permute 4, and we'll hit enter. And there you are, 116,180, what we get here in this. Any questions about that? Any questions about the calculator here? Come back and use it again. Be sure everybody's good with that. Can I do that again? Sure, I can do that again. So hit 20. Okay, so let's type in the number 20, hit the math key, go over to probability. So go over to the probability submenu. Okay, so notice how this is highlighted here at the top, natty, PROB function. And then you just want to scroll down to number 2 here, which says NPR for permutations. And then hit number 4 after that, and then enter. And there you should have gotten your number that we're after here for this problem. Did you get that? What does that represent? So this represents that there is 116,280 ways to select a committee of 4 from 20 people. Okay, given that we have to put each one of them in the respective spots. So that is exactly what it represents. Oh, okay. All right, cool. All right. Let's do the next part here. So understand that this is with permutations. Now let's talk about its counterpart here. All right. And so let's go ahead and go to combinations. Okay. So what is a combination? So a combination is the number of arrangements of R things chosen from a pool of N things where order does not matter. And it is equivalent to this, as you see, NCR. And there is a slight difference here, but it makes a significant difference actually. That is equivalent to n factorial over r factorial times n minus r factorial. Again, repetition is not allowed here for this. Okay, so as what we have here in this instance. Now, Having said that, of course, let's go ahead and take a look at our example here. Let's see exactly how we can go ahead and figure this out. And we're going to do an actual practical example here, a real one. All right. So what example am I going to choose here? Let's pick one of my favorite examples here for combinations. Combinations used a lot in stats. So let's use the lotto. Okay. How many of you guys how many of you guys have played the lotto or played like Powerball or maybe bought a lottery ticket? No. Have you guys ever spent any money on lotto tickets? Maybe you have. Maybe because the jackpots are super high, maybe sometimes you buy a lotto ticket. Yeah. Nah, never. No? Fair enough, fair enough. Sometimes some people do. It'd be like, "Hey, it's nearly $1 billion. Why don't I just buy a lotto ticket just for the heck of it?" Like, yeah, okay, well, fine. Okay, some people, yeah, some people, nah. All right, that's fair. That's fair. You've bought a lotto ticket before in the past. Hopefully, you're like, hey, I could possibly win. So, all right, now let's take a look at one of the lotto games here. Even if you've never played lotto, uh, let's take a look at one of the games for lotto here in the state of Illinois, at least. Let's take a look at Powerball. Okay, let's take a look at Powerball here. All right, so I'll actually make. Wait, why did I do that? Wait, I picked the wrong thing. Okay, hang on. That turn off. I want to turn on Java Dark Reader. All right, there we go. Okay. In any case, so how does Powerball work? Powerball works is that you'll get to select five numbers from 1 to 69. Nice. For the white balls, and then select a one number from 1 to 26 for the red Powerball. Okay. And if we match all five of the white numbers and the Powerball number, then of course we win the grand prize. Okay. So that's pretty much how Powerball works at this current moment in time. So let's take a look here on how this go. Okay, so let's at least put it here. We have 1 to 69 for the white balls, again of which there are five of them. 5. And 1 to 26 red ball, of which there is just one. Okay? That's what we have here so far. Now, let's take a good look here at each one of these slots. Like so. Okay. Now, let's go ahead and talk about one thing here. Now, let's say you buy a lotto ticket. If you buy a lotto ticket, one of the things on the lotto ticket is that regardless of whatever ticket that you buy, it'll be put in numerical order because the printing machine will just put it in numerical order no matter what things you filled out. So it'll just be like, okay, hey, you put it in numerical order, that's fine. So maybe on your ticket there, you're going to see 1, 2, 3, 4, 5. Okay, so maybe on your ticket there it may say, like, for example, 1, 2, 3, 4, 5. That's fair, right? Now, when they do the drawing for Powerball, there's like a big bucket of numbers, okay, and those bucket numbers are like revolving around or whatever, and then either the machine will let it go, or again somebody will reach in and pull it out, whatever the case may be. But five numbers are randomly selected from a bin of 69 numbers here from 1 to 69. All right, let's say for example here the numbers here that come out. Let's say it's 25134 or 24315 or maybe 31254. Okay, so let's say we have these guys here. Now here's a question for you. Let's put a little poll here. Let's put a little poll here. Put a new. Okay. Okay. Let's put a quick poll here. So quick poll here says, just look up above here. It says, are these the same? So essentially, is 1, 2, 3, 4, 5 in the lotto the same as 2, 5, 1, 3, 4? Is it the same as 2, 4, 3, 1, 5? Is it the same as 3, 1, 2, 5, 4? Are these the same? Go ahead and mark down yes or no of what you think, if these are the same or not in this particular lottery situation. Give you a minute here to think on it. So, think that these guys here are the same, or are they different? Are all these four guys here the same or are they different? All right. And this one's a tricky one here, so and I can understand. So some people say, have a lot of people say yes. We have 3 people say yes. We have 5 people say no. That's okay. And give it a think here. Are these the same? Yes or no? Got 25 seconds here or so. All right. A few more seconds here. We'll see exactly what the vote count's going to be. All right. Okay. So we have 5 people say no and 4 people say yes. Well, let's go over the answer here and see if we're correct. So the answer is yes. The answer is yes. These 4 things that you see here on the screen, these are exactly the same. There is no difference between 1, 2, 3, 4, 5 and 2, 5, 1, 3, 4, for example. There's absolutely no difference. Now, you're probably saying, whoa, 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 time out. These look different because they're written a little differently. Well, this is where the other part of combinations actually comes into play. Remember, in combinations, order does not matter. Now, in this instance, why is in a lottery game does order not matter? Why does order not matter in a lottery game? The reason why order does not matter in a lotto game specifically is because in lottery, all you need to do is match the numbers and then you win. Okay, so you match the numbers. So, say for example, you have 1, 2, 3, 4, 5 on your ticket and you're watching the drawing, and the first number comes out to be a 2. Well, you just need to match the number on the ticket. So, do you have a 2 on your ticket? Well, you're like, yeah, I do. Okay, great. Okay, I matched the number. Maybe the next number comes out as 5. Do I have a 5 on my ticket? Yeah, I do. Okay, great. Next number comes out as a 1. Do I have a 1 on my ticket? Yes, I do. Okay, so now I got a 1 on my ticket. Next number comes out as a 3. Do I have a 3 on my ticket? Yeah, I do. Okay, great. And that last number comes out as a 4. Do I have a 4 in my ticket? Yeah, I do. Okay, great. Now I've matched all 5 numbers. So it didn't matter when it came out. As long as it matched the numbers that I have on my ticket, then I'm a winner. So order here does not matter. Now, of course, this has some grave implications. Grave implications indeed. The thing is that we don't want to count this same combination 4 times. Since this is the same, we are wanting to get rid of many, many repeats. It's 1, 2, 3, 4, 5, and 2, 5, 1, 3, 4, and all these guys are the same exact thing. We only want to count that once, and we never want to count it again. So that's where you see this extra part here of this r factorial come into play gets rid of all those repeats that we would have here, or say something like 1, 2, 3, 5. All right, so in reality, what we have here is, what are we looking at here in this instance? What we're looking at here specifically is we're looking at 69 choose 5. So a common thing that we say here in math is we call it 69 choose 5, is if we're combining something, combinations. So 69 choose 5. And then we'll multiply that by the red Powerball here. There are 26 possible Powerballs. So we'll multiply that by 26. Okay, so we have 69 choose 5, and we'll multiply that result by 26. Let's take out our calculator here, and let's do this together. See how many possible combinations we have here for the Powerball. All right, so we have, again, 69. Hit the math key here. Over to probability. Go to NCR this time for combinations. 69 choose 5. Multiply that by 26. Go ahead and hit enter. And this is equal to 292,101,338. All right. So 292,201,338 possible combinations for lottery. So what's your chance of winning here in the lottery? If we talked about probability, your chance of winning the lottery is 1 out of that 292 million. So we talked about the odds of actually winning the lottery. Actually win the lottery out here. I could do that. All right, so here we see our actual result here of our odds. If we want to say what's our odds of winning? Okay, well, it's 3.42 times 10 to the negative 9th power is basically our odds of winning the lotto, right? Or 1, 2, 5, 6, 7, 8, or 2. Or if you're looking at it as a percentage, 5. So if you want to look at an actual percentage here of winning the Powerball, is 0.000000342% to winning the Powerball. Yeah. So your odds of winning the lotto here are rather low. Not bad. Not bad, eh? Yeah, not too bad. Not too bad to win the lotto. This is why I don't play. Well, you can play instant tickets. I mean, instant tickets are a little bit of a better draw. So I don't know if any of you played instant tickets before. So have any of you played instant tickets? Those are the scratch off tickets, camera. Basically the ones where you scratch and then you see if you won or not. Okay. Well, let me show you something, Natty. I think this may actually interest you here a little bit. So let's go ahead and take a look here at the Illinois Lottery website. So So there's the Illinois Lottery website here that we can actually go to. And so, of course, at the Illinois Lottery website, you can see previous results. You can play even online these days, or whatever. But what we're going to go to is we're going to go to the instant lottery results. So let's go games. We're going to go over to instant tickets here. And one of the things underneath instant tickets is by law, they have to tell you exactly what prizes are claimed and not are unclaimed, pardon me, as part of their prize pool. All right. So this is basically a recap of what's currently, it's updated every single day. All right. About games that are currently being offered by the Illinois Lottery. All right. And if you want to actually skew, um, basically, if you want to give yourself a slight advantage on certain instant tickets, you can. Now, how do I do that? Well, the thing is that every every game that you play, no matter what, has a finite number of tickets. Okay, the finite number of instant tickets. All right. So because there's a finite number of instant tickets, all right, and that finite number goes down over time, all right, then the number of unclaimed prizes, if that happens to be a bit high, all right, in a game that's been circulated for a while, then that should give you a good idea that maybe that game is a good game to actually buy an instant ticket for. So, for example, what would be a good game to buy? A good game to buy is this game right here, which is 5 times the cash. Why is this a good game to buy if you were to go to like a grocery store or the gas station? Well, because the fact that you have 5 remaining prizes that are worth 10 grand. You have 8 out of 10 that are worth 1,000. This game has been only out 10 weeks, but 10 weeks is quite a long time to be in circulation and get a lot of those bad tickets out. At least you hope so. So, again, am I guaranteeing you to win? No, I'm not guaranteeing you to win, but I am saying you can strategize and choose which instant tickets you wish to buy before actually going and purchasing them and seeing which ones are better than others. So you can see here, looks like it's a little bit less than half of the prizes have been taken here, which means you have a pretty good chance in a limited pool to actually get a prize. Well, hopefully anyway. This is a decent bet here because this is a brand new game of blackjack, which looks like it just started. So looks like all majority of the prizes here are still there, but still, that's a decent one to do. It's not the greatest since it just started. What are some poor ones though? Well, here's one that's pretty poor. Like in this case here, this is pretty poor because of the fact that you have one prize that has $10,000, half the prizes of 1,000, and you only have 4 out of 40 for 400. So your odds of winning a nice prize from the $10,000 jackpot $1 game isn't going to be as good because the prize pool is actually significantly lower since most of them have already been claimed. So there's ways you can read into this and basically say, hey, these games look pretty good because there's still a significant prize pool that I can still win off of. Do I guarantee you're going to win? No. But can you at least move the odds slightly a little bit more in your favor to hopefully get a winning ticket? Yes. Yes, you can. All right. So, again, you can read into it a little bit, and this is updated every single day on the Illinois Lottery website. So, a way that hopefully you can possibly win there at the gas station. You have any questions about that, anybody? I know. Yeah, so one of the things about statistics is that strategizing, even for something like instant tickets, is actually plausible, even if it still doesn't guarantee you a victory. If you can eke it just a little favor, it's not so bad. Okay, rather than just kind of picking and choosing. Oh yeah, that ticket looks nice. Like that ticket looks nice is like the worst thing to do. Or yeah, this $30 ticket's gonna net me the best odds of winning, like, or the best rate of return. Like, probably not. Okay. So something to keep in mind. All right. Good stuff. Ain't terrible. All right. Have I ever won anything in the lottery? Yeah. Actually, on an instant scratcher a long time ago, I won like $100 on an instant scratcher. So that was a long time ago, though. I was in my early 20s when I did that. Yeah, like $100. So yeah, the luck can be on your side. You can actually affect the luck to be on your side, though, as opposed to being a random $100 winner. You can actually change the luck to be slightly in your favor. Slightly. I won't say great, because it's still an instant ticket. But at least the luck will go slightly a bit more in your favor. Better than zero, that's correct. Better than absolutely nothing. Looks like you buy some instant tickets. Respect, Susan. Just yeah, just you can troll through this website. You can troll through the Illinois Lottery website, and you can again pick and choose what tickets you want to buy. Write those type of tickets you want down, whatever is within your budget, of course, of whatever you want to spend, because there's different tiers of tickets, like $1, $2 tickets, or whatever, and then go ahead and buy them. Like I look at this one here, Winter Double Match. What a terrible ticket. Okay, absolutely horrible. I would never buy this. Right. So I wouldn't buy this because there's no jackpots left. So like, why would I buy that if I'm never gonna jackpot? So I'd buy better. I'd buy better tickets than that. So pick and choose. It's not bad to strategize sometimes. Okay. All right. Not too shabby crabby. Righty. Good beans. Okay. Let us. Okay. At least you guys now have a good idea about how I select certain things. You're like, oh, there's an actual yeah, if I go and get instant tickets, if I go back and get an instant ticket, this is the way I'm going to buy my instant tickets. I'll strategize beforehand and then grab some instant tickets, and then we'll see what we get. So how about we, if you want to do that, you can. I'll do it. I'll do it myself. I'll tell you what. I'll tell you what. I'll go do it myself. I'll get some of these instant tickets, and then we'll see what happens. I'll buy like a few, and then we'll see what happens. Again, law of averages. I don't know. I don't expect to win anything, mind you, but I can go out and spend like $10, $20, or get some guys, some of the cheaper ones. So that's why. A very expensive. I haven't looked through this site in a while. Let's see. Pay me for $20. Pay me. All right. Oh, that's a rough game. Hydration. Today I have Dr. Pepper from Kentucky Fried Chicken. So, yes. Perfect. Wow. 25 bucks a diamond crossword? Yuck. That's no. That ain't terrible. Alright. Anyway. Keep judging things. All right, stop. Keep judging my odds. Anyway, fun. All right, any questions about the lotto? Any questions? Any questions? Any questions? Nope. Nada. Not a thing. All right. All right, let me quickly ask you guys really quick. I'm going to ask you, is it okay if I forego the break, but I let you out a little bit earlier? That sound okay to you today? We don't have too much more to go, so I just got a couple quick examples to show you here. So if it's okay with you guys, I'll show you those couple other quick examples, and then I'll let you guys go early, so easier on you. So, all right. If you've given me permission, then I will go with that. All right. Perfect. All I need is permission. All right. So let's look at the last couple of questions here on this handout. Okay. So that. Okay. So we're going to take a look at some more probabilities, and we'll take a look at question 5 as well. Oh, yeah, I actually. All right. So I'm going to look at a particular problem here in the book for us to go over. So let's take a good look here at number 62. Okay, so we'll look at 62 here, where we're actually going to go ahead and apply probabilities. First and foremost here, so suppose that there are 55 Democrats and 45 Republicans in the U.S. Senate. A committee of 7 senators is to be formed by selecting members of the Senate randomly. Let's look at letter A. So let's establish what we have here. We have 55 Dems, all right, and 45 Repubs. Okay, we have to form a committee of 7. So we have a committee of 7. So let's look at letter A. Letter A is, what's the probability that the committee is composed of all Democrats? Probability of all Dems. Okay. Actually, I'll put all of them. Okay, so let's talk about how we can find this particular probability. So we have to figure out how many combinations that we're going to have here, okay, for the all Democrats. Now, the reason why I say combinations here is because if we're picking 7 Democrats, well, it doesn't matter how we pick those 7 Democrats. Each one of those Democrats that we select in this committee don't necessarily have a particular position to go into. As far as we know, they're all equals in this committee, and there you go, they talk about whatever. So let's think about it this way. How can we express how many ways is it going to take for us to select 7 Democrats here? What is that going to be here? Combinations to select 7 Democrats. What do you guys think? How many ways to select 7 Democrats? Well, how many Democrats do we have according to this problem here? Let's at least answer this question first. How many Democrats do we have here according to this problem? 2,475 ways? How did we get that there, Beth? How did we get that here? 55 times 45. Not exactly here. Look at it carefully. We're selecting 7 Democrats. Let's answer this question here one piece at a time. So answer this question first. How many Democrats do we have? How many Democrats do we have? All right, we have 55 Democrats according to what we have here, right? We have 55 Democrats. All right. We have 55 choose. So we'll go 55 choose. I can see right here. How many are we selecting out of the 55 to make up this committee? How many out of the 55? 7. That's correct. 7. So we have 55 choose 7 here as part of our numerator. Okay. Let's at least let's talk about this here carefully. Again, what does this represent? All right. So this represents, again, selecting selecting 7 people from the pool from 55 Democrats. Okay, so from the pool of 55 Democrats. Now, let's look at it from overall, because we take a probability, we have a number divided by another number here. So we have to divide it by something here. So what the denominator here for this is going to be is the total number of ways to select 7 from the Senate, from the whole Senate. Okay, so let's talk about it this way here. How many total people are in the Senate? How many total people are in the Senate according to this problem? How many total people are in the Senate? 100, right? So we have 55 plus 45, going to be 100 people total in the Senate. And how many are we choosing? Want to figure out how many are we choosing again? We have 100 choose how much? 7. That's right. So let's take a look at what we have here. In the numerator, we have 55 choose 7. So again, that's because of the fact that we're selecting 7 people from the pool of 55 if we want to follow all Democrats. Out of 100 choose 7. That's the total number of ways that we can select a committee of 7 from either party. Okay, so it doesn't matter what their party is. It's just we have a pool of 100 people and we're picking 7 from them overall. Okay, now we just want to enter this into a calculator and let's see what we get. So on the calculator here, I want to do this out. Just going to have here, let me click. I'm going to have 55 and then math. Go over here. Go to NCR. 55 choose 7. Divide that by 100. RB 100 choose 7 here. Okay, so here we get 0.02, so 0.0127. Okay, 0, 1, 2. Okay, Are there any questions about that? I want to be sure everybody's on the same page here about how we found part A. Any questions so far? None? Okay. All right. All right. So we have a template here about how things will work for probabilities, okay? Now let's take a look at two more scenarios here using this same type of template, all right? So let's look at letter B, all right? So letter B says, and I'm just going to read this off here. What's the probability of all Republicans? So all Republicans here, all Repubs. What's the probability that this committee is made of Republicans? Okay, let's put this together here. This will still be 100 choose 7 here on the bottom. Okay, that part is not going to change because that's the total number of ways we can make a committee of 7 from the 100 people in the Senate. How about the top part there? What are we going to put for that? Oh, right. Very nice. Yes, that is correct. 45 choose 7. Okay, so we have 45 choose 7 here. All right, so now let's put that on a calculator, and then you guys tell me what you get. We have 45 choose 7 is correct. We're picking 7 people out of the pool of 45 Republicans. All right, we'll divide that by 100 choose 7 there. You guys tell me what you guys get. 0.00283, okay. All right, good stuff. All right. Nice job. That is correct. Very good. So that's part B. Part B. Let's move to part C here. Third part to this. So in reality, probably it's very low likelihood that we're going to have all Republicans or all Democrats. Instead, we're going to probably have a mix between the both. So what's the probability that we have 3 Dems and 4 Republicans? So 3 Democrats and 4 Republicans, all right, on this committee. Now again, I'll just assure you once again, the bottom part here is not going to change. All right. So what are we going to put up top here? We're going to put up top. Got 100 choose 7 here, but what are we going to put up top? $55 choose 3 times 45 choose 4. Okay. All right. And that, my friend, is okay. 55 choose 3 is correct. All right. And I will also agree with you, Mazdi, absolutely 100%, my dude. It will definitely be 45 choose 4 as well. Now, notice here, I want you to notice here, everybody, that notice we did put multiplication between those two. That's correct. Okay, we're not putting addition here. We're putting multiplication. So we're using the multiplication rule here in this instance. How many ways can we select 3 from the 55 times how many ways we can select 4 from the 45? All right, so not addition, multiplication. All right, so make sure you don't fall for that trap in this. So we're going to go ahead and plug that into the calculator there. And then I want you to go ahead and give me an answer once you have that plugged away. Does anybody have an answer? Yes. Point 00698. Wait. Go ahead and not quite with that one. Remember, a 55 choose 3. Okay, so we're going to choose 3 here. And then we'll multiply that by 45 choose 4. Okay, so don't forget you have to multiply that by that, then divide it by 100 choose 7. So it should look just like this, Beth. Right, so just making sure that you have that entered in correctly. Just like so. You can even put parentheses around this here, if it helps. So, yes, that is correct. 0.2442. Oh, you used NPR, yes. Yeah, be sure you use the combinations here and not the permutations. Remember, order doesn't matter because Jim, Mary, and Bob are the same thing as Mary, Bob, and Jim. Okay, so it doesn't matter how you view this committee since there's no rhyme or reason behind that. We're not using permutations here. We're using combinations here. Okay, so order does not matter because we don't have particular positions that we're filling in. Okay, good, 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 good. All right, any questions about that example there? Examples can be a bit tricky, so I wanted to go slow over that so you can see exactly how that works. Right? Okay, now I'm going to take a look at one last example here at the very least. All right, good, good. Let's go back to our handout here. We've talked about combinations here so far, but let's talk about number 5. I have an example right here already. Go here. Down a bit. Wait, wait. It actually worked. Okay. All right, so number 5. What are the number of permutations with non-distinct items? So the way this works is that we have a number of permutations of n objects. So essentially it's like in our example we have, say, a number of flags, and each flag is the same manufacturing. Maybe you have different colors of flags, but you're trying to arrange the flags with flags that have the same dimensions and colors and everything associated with it. So you have non-distinct items in this particular instance. So the number of permutations of n objects of which you have a of one kind, b of another kind, z of a kth kind here is given by n factorial divided by a factorial, b factorial times dot 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 times z factorial, where n is equal to a plus b all the way down to z, however long z takes you, whatever. So how does it work? Well, let's say we have a flag of 3 colors. We have green, red, and blue. All right, so the flag can have different arrangements using the colors. Say we have 5 green, 3 red, and 7 blue kind of flags here. All right, how many arrangements are possible of the 15 flags? All right, so how many arrangements are possible? We have 5 green flags. They look exactly the same dimensions, the whole 9 yards. They're not distinct in any way. 3 red flags, same deal. They're just red, but we have 3 of them. We got 7 blue flags. Again, no difference between the blue flags there. Everything is the same. Same dimensions, same whole 9 yards. This would be like one of those things that you would find at a birthday party, one of those flag things. Anyway, like that kind of decoration. How many arrangements are possible of the 15 flags? Right? So the way we do this is we have 15 factorial here. That's how many flags that we have. Divided by 5 factorial times 3 factorial times 7 factorial. And so if you go ahead and do that on the calculator there, you'll find out you'll get 360,360. All right? So there's 360,360 ways to basically permute 15 flags of which of non-distinct items, essentially non-distinct colors. So green, red, and blue here being the 3 colors, and the everything in the dimensions and everything that was manufactured being non-distinct for each one of those colors respectively. Right? And that's essentially how we do number 5. Now number 5 is not something we focus on too much. Okay, but it is one of those things that does pop up from time to time. Again, it's just like I said here, it's more along the lines of, hey, this is how we deal with things that kind of look the same. Most of the time, though, we deal with like things like the combinations side of things or permutation side of things because you get more probabilities based off of that. Okay, so that is, in a sense, the end of section 5.5. Now, due to the fact that this is the end of section 5.5, this is also the end of section 5.6. You're probably saying there's 5.5 and 5.6. That part is true. I said yes, that's true. The reason why is 5.6 does exist, okay? It does. The thing about 5.6 is 5.6 is just a recap section over everything in chapter 5. All right, so the book here is slightly a bit different. I think maybe the book, but there is like the next section here. It says, "Oh well, what do I do?" sort of deal. If I uh, go to page 1 of our table of contents. All right, so you can see here, section 5.6 is basically says putting it together. Which method do I use? It's just basically a recap section of 5.1 to 5.5. So all the questions there are just basically rehashed questions from the sections from before. Okay, so we're not going to do 5.7. It's just 5.1 to 5.6 here. But yes, so 5.6 does exist. It's just okay. It's just the rehash of everything from 5.1 to 5.5. So I'm not going to rehash everything from 5.1 to 5.5. That's already been talked about at extent, ad infinitum. So I'm not going to go ahead and just restate everything. They're just the same exact types of questions as you've seen from before. Okay, so just a little bit of added practice of what you've seen in chapter 5, but that's all it is. Some chapters will have these kind of recap sections into it, so we're not going to spend too much time on it unless there may be an example in there which I feel would be good to use in a given situation. So, which may come up. It just depends. So we'll see where it goes. In any case, that's how we pretty much do that. All right. So we're in effect done with chapter 5. All right. That is the end chapter 5. All right. Any questions about that? All right. And I can go back to the notes. Absolutely, Andy. Here we are. Now, which question you'd like me to go back to? It's number 5 anyway. You're welcome. Um. Oh, okay. Then we're there. All right. As I promised, I will let you go early here today. So I want to thank everyone for coming on out here to the stream once again for today. Thank you so very, very much for coming on out here once again. You guys are wonderful. Okay, for coming out here at 6 o'clock at night, coming watching a schlub like me. I appreciate that very, very much. You guys are absolutely outstanding. All right. Yes, I approve of this. All right, you guys are great. Okay. And I think we will definitely start here, chapter 6. Oh, thank you, Natty. I appreciate that. Um, we will start chapter 6 on Wednesday. Okay, Wednesday. We will come back on Wednesday. Okay, a couple days from now. In the meantime, everyone, continue to enjoy your week. We'll see you in a couple of days. And no, thank you for being you. Okay, thank you for being good for great people who want to sit in, listen to a guy like me. You guys are great students as well. Okay, like I said, we're working on being successful. That's what we're working on. All right, let's do it. Let's do chapter 6 on Wednesday. Have a great 48 hours, everybody. We'll come back here, same time, same place, everybody. Take care of yourself. Have yourself a wonderful night. All right. All right. Everyone, let's see, what else do I want to say? Yes, there's one more thing I want to say. I want to say, yes, stay safe. All right, stay safe out there, everybody. Stay healthy, and most importantly, everybody, stay sane. All right, have yourself a wonderful night, and we'll see you on Wednesday. Take care, everybody. All right, have a good one. Bye.